Hear me?
Yes, we can hear you. Now we will check the sound. Please say something. We can hear you. We can see you very well. Danilo, could you please connect your micro and say something? We just need to check the sound. Hello, everyone. Good morning, good day, good evening. We will start in a few minutes.
Hi, Julia. I'm sorry, I was muted.
Yeah, now we can hear you very well. Cool, thank you. As I said, we will start in a couple of minutes. Let's wait for all speakers. They are connecting. Just for everyone who are joining us, you are very welcome to use chat to ask questions. You can use the question and answers settings and raise your hand. So by now we have a good sound and everything is okay. We will start streaming to LinkedIn as well and YouTube channel. So for everyone who will join us through LinkedIn, we will start in a few minutes. Ilya, I don't see you here. Please join us and say when we will start streaming. Now my colleagues told me that we are already streaming to LinkedIn. So good evening, everyone who joined us through LinkedIn. So we will start in a few minutes. I guess Blair joined us. Blair, we're checking the sound and
yeah, can you hear me? Okay.
Okay, yeah, we can hear you, but we cannot see you. Anyway, we have 5 minutes to start. Meanwhile, our attendees are joining us, but we can hear you very well. Okay, let's
I think the use, I'm looking at the presentation, we'll update this because it has my name instead of Andrew's name. Also, we had just...
We're already on the stream, so I will help you now in chat. And we have just a couple of the minutes, 4 minutes to start. Okay.
Are you gonna share my presentation, or am I sharing the presentation? Because I see some changes are missing that we discussed yesterday.
I will send it to you right now.
I downloaded the one that you did this morning. Also, I think I have the slide that you did this morning, but I think slide 17 should be hidden because those.
Blair, we are already starting, so let me share with you. And we're already on stream, so our participants are joining us.
Mm-hmm.
Okay, I think we are ready to start. So once again, good evening, good morning, good day. Thank you for joining us tonight or today. Please, Blair, take your turn, and I will stop to share the screen, and you can share your screen. Hello, everyone. Bill, yes, you can hear us. Okay, thank you for joining us. Hossein, Dr. Promet, hello. Nice to see you here. Hello, Rohan. Hello to everyone. Hi, good day, Jonathan. I just would like to remind that a lot of people are joining us through the LinkedIn. So we will also try to answer your questions there in the chat. And now we can start.
All right. Hello, Yulia. Are you able to see my screen at the moment?
Yes, we can see your screen. Everything is perfect.
All right, excellent. All right. Well, then let's, if I may, I can get started by welcoming everyone to our event, Big Revolution in TinyML. Certainly for myself, just by way of introduction, my name is Blair Newman. I'm the CTO here at Newton, and I'm certainly glad to have an opportunity to share with you guys not only our view as it relates to TinyML, but also have the opportunity to introduce a number of different experts in this particular area that I'm certainly sure that all of you guys will get some value during the course of not only today's event, but over the next couple of days as well. So with that said, we can get started. One of the things that I've learned when it comes to TinyML is TinyML, of course, it covers a number of different, I would say, skill sets. We have a number of different experts or individuals who may have an expertise, let's say, in embedded engineering. We have some experts and participants who may be very well experienced in machine learning. We oftentimes have some individuals who are just new to the TinyML field overall. And for me, that's one of the beauties about TinyML is that it covers experiences and it covers expertise from a wide range of fields, which actually for me, and certainly for us here at Newton, it certainly creates an opportunity where we can not only participate, but we can help provide value in a number of different areas. So I like to oftentimes start off with that because as I began to have an opportunity to speak with a number of individuals, it's often at times important to kind of level set or kind of come to a common understanding as does what does TinyML mean for everyone. So one of the things that I like to do is kind of align on what our view is as it relates to TinyML. And I'm sure our participants, not only today, but also over the next couple of days, will also share with you where they're focused at in this particular area. And when you begin to look at TinyML or edge computing, one of the key areas is how do we begin that process of really connecting the physical world with what we like to call the digital world. And in doing so, what we like to do is we want to accomplish being able to bring some significant intelligence into the physical world and make that particular connection. And that's one of the areas that we focus on here at Newton, is we really enabling both of those two worlds to be able to connect and ultimately bring value, whether it's to yourself, whether you're working in research, whether you're on the business side. And I believe that we have a number of different experts throughout our event that will be able to share that experience. But where we really find where we bring a tremendous amount of value is connecting those two areas, whether you're working on the embedded side, whether you're building physical devices, whether you're working on the machine learning side. This is an area where we believe from a Newton perspective, we really kind of connect the two dots, connect those two worlds, and ultimately enable you to accomplish your tasks and objectives as you move forward throughout your particular journey. Now, one of the areas that we like to start, where we find that it's oftentimes an area I like to say of opportunity. When I look at, let's say, the TinyML community, we tend to find that at the moment, there's probably more resources or experts, let's say, on the embedded side and on the hardware side. And now they're faced with that challenge of being able to bring intelligence to that physical hardware, whether it's a sensor, whether it's an IoT device, it really doesn't matter. Now, in doing so, there's a couple of different challenges that we're oftentimes faced with. You know, does an organization have that data scientists available so that they can enable their devices with the necessary intelligence to accomplish their particular projects and goals? And in doing so, if you are familiar with machine learning, or even if you're not familiar with machine learning, historically, it's been an extremely manual approach. It's been an extremely iterative approach. And needless to say, of course, you oftentimes need to have an extremely high level of expertise available in your organization to be able to produce the necessary models to integrate those models into your devices. And then, of course, if you're fortunate enough to have those resources available within your organization, and you take that first initial step of being able to create a model that you find that operates at your expectations, then you need to take that next leap, that next step, and say, now, how can I now integrate this model into the hardware that I've decided to work with? And we found that traditional models are extremely large, and they don't oftentimes fit the requirements from a physical perspective to be able to integrate into those devices. So we're faced with performing a number of different tasks, from a compression perspective. And there are tools that are out there, such as TensorFlow Lite, et cetera, that you can take advantage of that can help you accomplish that goal. But one of the things that we also learned is that when it comes to TinyML, the size of your models, the amount of power that you're consuming, that is ultimately your currency, because you want to be able to make sure that you have a model that's not only small, but is extremely efficient, so that you're not consuming all of that valuable real estate that's on your hardware device. And one of the things that I like to show here is that not only is it's an extremely manual process, but it also oftentimes can take an extremely long amount of time. So if you're a business user that is out there and you're worried about the time to market, that's one of the areas that you have historically have to be concerned with. And then, of course, once you produce that model, then you need to begin to think about, hey, does the model perform as expected? Can I trust this model? And oh, by the way, when will I know if that model may begin to decay along the way, so that you can maybe potentially retrain that model? And we kind of like to look at this as the legacy approach as to how oftentimes TinyML, or the process of being able to produce models, have historically been followed. And Newton, we're taking what I like to say, we're really kind of flipping the paradigm on its head, and we're really taking a significantly different approach to enabling our partners, our customers, to be able to complete these tasks, and oftentimes, 70% of the time than what it would take you normally by doing it manually. So what's our approach? Our approach kind of follows really three very critical steps. Number one is we want to be able to enable all of our partners, all of our customers, to be able to produce a model efficiently. And this is where we begin to talk about accelerating your go-to-market. So when you begin to take a look at Newton is a zero-code AutoML solution that enables you to produce models efficiently without compromising accuracy in one iteration. You may recall, and even for those individuals who have experienced yourselves building models, it's an extremely iterative process. You go through, you build a model, and you look to try to validate if whether that model meets your expectations from a business perspective, as well as from a technical perspective. And this is one of the areas that, quite honestly, we truly excel at. So all of the models that we build, we start out by building all of our models neuron by neuron. We don't start out with an existing structure that ultimately ends up with a lot of waste, where you have to go through compression, pruning, distillation, etc. We've eliminated all of that. So as we build all of our models neuron by neuron, we perform cross-validation along the way, so that by the time you've reached your model, your ideal level of accuracy, you do not need to perform any compression along the way. So this is where we say we enable our customers to build fast, because you don't have to go through that iterative process, number one. Number two, you only have to go through one iteration. And then lastly, when we begin to talk about never compromising, this is the area when we begin to talk about our explainability office. Our explainability office gives all of our customers, all of our partners, the transparency that they need to see into all of our models. And in doing so, We also provide a lifecycle management tool for all of our customers so that they can proactively identify if there's experience in any model decay and they may need to train their specific model. So this is the approach, really kind of a three-step approach, and really highlighting the three fundamental areas that we have found that our customers find extremely valuable. Now, what's some of the results? What's some of the value that you can get out of our platform once you have had the opportunity to take advantage of our platform? We have found that consistently, all of our models oftentimes are up to 1,000 times smaller than what you may find from other competitors or other frameworks that are out there. And in turn, being able to produce a model that is extremely compact. And as I mentioned, we're not compromising accuracy along the way. You also find that you're going to have a faster inference time when you come to running your predictions, et cetera. And of course, with these compact models, they're going to run much more efficient on your devices, on your microcontrollers, or whatever you're using as it relates to, to your particular project. So that's another area that we are extremely proud of. Now, when we begin to talk about TinyML, and I've had the opportunity to speak at a number of different TinyML summits, there's certainly aspirations and goals that we will find millions, if not billions, of devices in our future that have intelligence. And one of the areas when we began to have a number of different discussions with various individuals throughout the industry, we begin to look at what are some of the key challenges that are out there that is preventing the acceleration and adoption from a TinyML perspective. Certainly, the ability to be able to build models efficiently, or the number of different data scientists that are out in our ecosystem today, is extremely limited. Number two is being able to make sure that you have a model that is not only accurate enough in order to meet your business expectations, but it also can integrate into your respective devices that you're taking advantage of and leveraging into your particular project or your particular implementation as well. And then, of course, lastly, from a business perspective, we want to be able to make sure that we understand how our models are executing, why they're making the predictions that they are making, and then, of course, as I've mentioned, being able to determine, hey, when do you may need to take the next step of retraining. So we also address this component by providing a complete lifecycle management tool for anyone that we may have the opportunity to work with. So hopefully that kind of gives you guys a really good overview and foundation as to what we're doing here from a Newton perspective. And certainly one of the things that we want to do, because of course, being able to enable the community is not only key to our success, but is key to everyone's success. And that's one of the key reasons why we've decided to host this event and bring forward to all of you guys a number of different experts over the next couple of days that certainly all of you guys will, I believe, get an extreme amount of value out of. Now, one of the areas that I've mentioned is that TinyML covers a number of different areas. Of course, it not only covers the hardware side, but also it covers machine learning, et cetera. And also one of the things that I wanted to share with you guys is that it covers a number of different areas as it relates to experience. So when you begin to look at today's agenda, we'll start off today. Today's agenda will be kicked off by Danilo Powell, where he'll be covering handcrafted ML design methodology and the challenges that it poses. And I'll introduce formally Danilo in just a moment. From there, we'll have Sumit Kumar, who will be talking about one of the use cases that has been implemented. He's been able to implement from an agricultural perspective. And then also for today, you'll be joined by one of my colleagues who will give an overview as to how you can be enabled, as I mentioned before, to be able to produce these models in 3 very simple steps along the way. Going into day 2 will be the beginning of where we will offer a number of different master classes that we will make available to all of you guys. So number 1, we'll share experiences on the hardware side, also on the implementation side. And then from there, we'll go into a number of different days where you'll be able to take advantage of a number of different areas. So starting first with Shuram Anubna, we will have a master class on the TinyML creation on TensorFlow. Specifically, we'll be talking about classification. During this day, also, there will be a competition that we will make available so that you guys can participate and receive some goodies, if I'm not mistaken. Day 3 will be a masterclass by Dr. Pramit on regression and front-end ML solution. We'll be talking about ML-based ML model-based APIs and a front end with Streamlit. And then wrapping up with day 4, there will be a masterclass on the end-to-end process of creating and embedding TinyML models on a microcontroller leveraging Newton. And there'll also be a competition award that day. So to kind of wrap up the week's events. Now, one of the areas that I kind of like to mention is that our idea, our focus with today's event, or just this event in general, is we kind of want to take you through the entire life cycle. So when I talk about the entire life cycle, it is really from beginning your journey as it relates to maybe what you're deciding to do, your decision-making from a hardware perspective. And we're going to end today with showing you an actual implementation of being able to develop a model and embed that model by leveraging Newton along the way. So that's one of the areas that I really want to encourage you guys to stick around for so that you can really grasp and see in real life and a practical example as to how you can take advantage not only of Newton, but also bring value to your organization. So let me just quickly give an overview as to our speakers today. So starting first, we will have Danilo Powell. Danilo Powell has a significant amount of experience in this particular field. He has been with STM Electronics since 1991. So he's extremely experienced. He's been involved in over 75 to 80 patents, over 120 publications, and he's authored well over 100 documents. And he have had a tremendous amount of experience as it relates to participating in these events. And I'm sure he'll be able to bring all of that experience that he's had over these years into today's discussion. So we're certainly honored to have Danilo to participate with us here today. And then also we will have Sumit Kumar. As I've mentioned, we'll be kind of bookending, or you'll also have the opportunity today to be able to see everything in action. So I believe Sumit will be kind of taking us through not only his experience, but also more importantly, how he's been able to successfully implement his particular project along the way. Now, one of the things that I like to share is that, and again, I don't mean to be repetitive, but our objective is to show, hey, how can you begin to take advantage of TinyML if you have, an exceptional amount of experience, let's say like Danilo, but then also how can you be successful, as Sumit? I mean, he's very experienced, but he's kind of just now beginning maybe his career. So we really wanted to show you the entire landscape, not only from a technical perspective, but also from a professional perspective as well. So I think that's also pretty awesome as it relates to the agenda that we've put together for you guys. Now, here are some of our instructors that we will have throughout the week's events. So we'll have Pramit Ray, who's a data scientist who will be conducting one of our classes that you guys will certainly have an opportunity to interact with and meet with as well. We'll have Shuram Anubna, again, a data scientist with a significant amount of experience that I believe you guys will enjoy extremely. And then lastly, we'll also have Soho Sharma, who's one of our data scientists as well. So we certainly believe that we have put together for you guys what I would call an all-star lineup. That's something at least here in the US we would say, meaning that you won't have an opportunity to find better people to interact with as it relates to their experiences and their successes and challenges and how they've overcome those challenges throughout their careers. So I certainly hope that you guys can find value in that as well. So with that said, I'd like to give you guys the opportunity to meet Danilo Powell. Danilo Powell is the technical director of IEEE and an ST fellow, and he's involved in system research and applications. So Danilo will be conducting our keynote speech. And so I will hand it over to Danilo so that you guys can begin to get value out of this particular event, much more than what I'm able to offer. So with that said, Danilo, welcome.
Thank you so much, Blair, for the nice, very nice introduction. Much appreciated the opportunity to speak within this event and within this community. And also thank to Julia and Anastasia for the very nice and awesome support. Let me share my screen, first of all, and okay, and go in slide mode. And just in a second, I will take my pen. Okay, nice. So today I would like to share my perspective on various challenges and various issues, but also various opportunities on automated machine learning design. And once again, Blair, I think this is a perfect place where to discuss this topic because I believe also you are bringing a contribution forward to what I think is the automated machine learning design gap. There is a gap, it's noticeable, and we will go through it and we will try to understand together why there is this gap and how can be fixed. By the way, I'm sorry if I wear the mask. I am in the company. This is compulsory. So apologize if you don't see clearly my face. So let's start with a few definitions. Let's start with automated machine learning, also known as AutoML. There is a theorem we need to remind. No free lunch, okay? There is no shortcut in saving computational complexity when trying to find a solution to a machine learning problem. If we average all of those in some problems in a class, the same cost is for any solution, okay? There is no escape on this. And furthermore, if I take a machine learning algorithm, obviously this will be characterized by different hyperparameters. And by varying the different parameters, the performances can vary very much. And this is known, is in the state of the art since 20 years. And therefore, when we started to design a machine learning pipeline, we need to select the model, to set and define a number of hyperparameters, and then selecting both, which is also known as cache approach. And all of those are ingredients to lead what is known as modern auto machine learning. Furthermore, we can define very easily automated machine learning as the capability to design automatically without ungrafting an algorithm, a pipeline, and setting both the pipeline and the hyperparameter in order to achieve proper and adequate performances on a given problem. And the problem is shaped by a set of data. When we deal with the subset of machine learning, the artificial neural network, AutoML specialized in neural architecture search. And now, the task to search the best pipeline for a given problem can be an amazingly complex task. Because, for example, I need to define a child model. I need to validate the performances of this chain model. And for who is familiar with k-fold validation, it can understand how complex is the process, especially if the data set is amazingly big. And then this has to be controlled. Control in the sense that we need to instantiate layers, key layers, convolutions, various kinds of convolutions, non-linearity, dense layers, batch normalization, and so on and so forth, in a pipeline with a certain topology and making choices in terms of hyperparameter, kernel size, stride, and so on and so forth, pooling rate, and therefore you can understand very easily how this is complex. And there are various methods in the state of the art to solve and to approach the optimizer for a given NAS approach. For example, reinforcement learning, or evolutionary method, or random or search which is based on some heuristics, or even more, optimization based on some gradient processing in order to find the optimal value of a fitness function. However, the de facto standard and the most known approach, which has been demonstrated since about 9 years on different tasks, is the Bayesian optimization, also known as a sequential model-based optimization. And this achieved very good performances on a number of open data sets, and since 2016, also beat competition set by human experts. This is quite relevant because it demonstrates that can be automated, can be accurate. And there are industry tools that support that. Some of those you certainly know: Google AutoML tables, Vizier, Amazon SageMaker, Azure Machine Learning. What is in common between those? These are cloud tools. There are also a number of open source projects. Some are of normal use, of common use: AutoQ Keras, Keras Tuner, NNI. Some of those are also based on Bayesian optimization, sometimes hybridized, and support both neural architecture search, hyperparameter optimization with a number of compression techniques in order to reduce the cost associated to a large inference model. The number of tools from an industry perspective are even more, but if you look carefully the algorithms that are supported, you see that some of those are really based on Bayesian optimization, which confirm what I was saying before, and that Bayesian optimization is the de facto approach which is dominating most of the solutions. Now, another thing that we need to pay attention are the supported frameworks. And certainly you recognize PyTorch, TensorFlow, Keras, Scikit-learn. And this is repeated. Some of those are not more actual, like Tian or Café2. These were tools in vogue a few years ago, but now not more of large diffusion by the AI community. So these different solutions clearly depict a scenario, a context, which is really rich in terms of solution. But what is the point? Well, let me look at this from the perspective of an embedded industry. A company like ST produces microcontrollers, sensors, and the associated silicon node technology for their manufacturing. So we are concerned with tiny devices, with devices that have got constrained resources in terms of memory, in terms of computational power, in terms of package size, in terms of also power consumption. However, when we use AutoML or NAS tool, some of those I just mentioned, we have solutions, we have pipelines that fit nicely in complex processor, what I call virtually unconstrained processors. Okay, which means that unfortunately they cannot be deployable on off-the-shelf, low-cost microcontrollers. And also the cost of finding those solutions is amazingly high. Accordingly to some open data, this is in the range that was estimated in the range of 40 petaflop per second per day. And this is just the training, okay? And this is clearly, this curve shows that is close to machine translation of speech, and even close to more complex approach. So let me play for a while with one problem. And my problem in this case is human activity recognition. I have an inertial sensor, which integrates an accelerometer and a gyroscope. I get some data, triaxial, with a certain data rate. I want to classify my activity. For example, given a carry position of the sensor, I would like to know if I would like to classify my activity as walking, running, sitting, standing, biking, and so on and so forth. What I would like to achieve is a tiny network. As I said, I am interested to implement such a model on a microprocessor. And if I handcraft the model, in my experience, that was about 40 kilobytes, can be even less than that, okay? Can be even tiny, depending on the data set. There are various data sets. This is one of those. There are other data sets like PAMAP2, SHL that can be used. But when I use AutoKeras and AutoML, then incredibly, I can get accurate solution at the cost of a quite huge model size. And this is not deployable, for sure. It's easy to understand. Therefore, this push myself on the current way to handle machine learning problems and craft topologies, okay? What I can automate is the deployment. So let me go through an example. The methodology that we introduced since 2017 to address machine learning solution in the context of supervised deep learning is composed by 5 steps. The first, which is typically handled by a customer of us, I define a problem. In the problem, for example, there is the definition that I want to design an intelligent microphone which recognizes some keywords or some short sentences, or my activities, or if I am a person, or a cat, or a dog, and so on and so forth. My hand pose, and so on and so forth. So I need to, so what's the point? I need to take a decision. I need to decide about a sensor. Can be an image sensor, can be a microphone, can be an inertial sensor, an environmental sensor, a gas sensor, and so on and so forth. There is a plethora of way to sensing the environment today. Okay. Second step is I need to get data because my problem is shaped not by a transfer function that I can write analytically, but it's shaped by the data that I can associate between that can compose input and expected output. Since I cannot shape the problem analytically, what I am left is with the data. The data capture a hidden transfer function that I need to approximate. Is hidden, so it's invisible to me, but I need to approximate. Given input, I need to approximate the output. How? I design a machine learning pipeline. For example, based on neural networks. So there is a plethora of tools, deep learning frameworks, TensorFlow, PyTorch, MXNet, Paddle, and so on and so forth. But at the end, there are 2 exchange formats that are de facto used by the AI community. TensorFlow Keras, which is a de facto standard, and the other is Unix. Then, if I want to take the results of a training, so a pre-trained neural network or a pre-trained machine learning pipeline, I need to deploy on my target execution device, which is a microcontroller. We do produce 2 microcontrollers. The family are called STM32 for IoT and SPC5 for automotive domain. What I should do, handcraft the solution. So I take the network, I know what are the layers, the meaning of the layers, and then I write my C code. Furthermore, I need to validate the C code because I would like, during the deployment, to achieve the same accuracy obtained during testing, following the testing of the neural network. Therefore, I have a productivity gap in the deployment, which is handcrafting the solution in C code and also validating. And in my experience, when I started to meet some at various fairs, some embedded developers, all of those were handcrafting by themselves the solution, which was a waste of time, a waste of productivity, and everybody were doing essentially the same task, writing their own library, optimizing, validating, and so on. This was highly redundant, not quite productive, and therefore we had the intuition, and we pursued the development of a tool that automatically converts in C code pre-trained neural network and validate them. These tools are called STM32Cube.ai for the STM32 family and SPC5 Studio.ai for the SPC5. And what was achievable in months now can be fully automated in seconds. Just an overview of the tool, but maybe it's better that I show you live. So what you see here, this interface, essentially is CubeMX. With CubeMX, you can download freely. You can pick up a microcontroller, in this case an STM32H7, and set the pins, set the clock, set the interface, and then add Xcube AI, which is the current version is the 710 that automatically pre-train the neural network. So I import my favorite neural network. I can analyze getting the complexity, getting the memory occupation, and also validating on the target where I essentially generated the code and deployed. And after the execution on a certain set of data, I will get a number of information. I will not go through all the information, but essentially one of those is a profiling, an accurate profiling on the target. So you can understand how can this be productive, because it's a matter of minutes to achieve this without a huge expertise. Now, validation is very important because any tool has not to reduce the accuracy that the AI expert achieved when developing a pipeline. And therefore, the C model need to make sure that the original neural network shows the same accuracy. Otherwise, it's a fault of the tool not able to demonstrate that. So it should be fully transparent in demonstrating, improving the accuracy for any data that the AI developer would like to test. Other features which are quite important, I need to remind. First of all, we introduce Keras customized layer. Why? I don't know how many of you are familiar with graphics, but one cornerstone in embedded graphics and in desktop graphics were the programmable shaders, because these freely let any graphic developer to express their creativity in differentiating the graphic pipeline and the graphic application. Similar to that, the Keras customized layer allows the complete freedom of a developer to differentiate the machine learning solution versus standard. And the tool need to be dealing with black box. Then it may be also that another expression of this freedom is to mix and match neural networks with machine learning. And we need that also to be supportive of the main library, which is capable to support a machine learning. For example, scikit-learn. And then also being able to feed, to provide information to any NAS tool in order to provide constraints. As I shown you, I can deploy immediately a pipeline, okay? And then measure the properties, occupation in RAM, occupation in flash, execution time. These set constraints, if a tool that does neural architecture search, consider them, can converge more quickly because it's optimized, knows what are the costs of the different solution is developing. And so not only concentrate on the accuracy, but also concentrate on the deployability. The tool we provided exactly provide those informations. So various memory constraints, various figures, profiling figures in terms of multiplying the accumulate per cycles, number of max per layers. So every time a NAS introduce a new layer, a new set of neurons can be supported by our tool in order to get the constraints and then freely decide what is the best way to control the evolution of the pipeline. And also it's important to have a nice, a proper memory allocator. Why? Because the microcontroller and the sensor are mainly affected by a huge restrictive amount of memory, very minimal RAM, very minimal flash. And these can be reduced a lot. And therefore, an allocator has to be capable to use as low as possible the memory during the scheduling of the different buffers, which are part of which stores the activations, the ways, the biases, typical of an inference pipeline. But there are also other things that need to be considered. For example, don't expect that a microcontroller has an homogeneous address space. There are the address space can be fragmented in pools, which are not consecutive in the memory space. So if I'm not able to manage properly them, clearly I'm wasting the capability to use those buffers. And therefore, I miss the opportunity to fit on those parts of the pipeline, which means I'm missing opportunity to deploy properly some solution that maybe are accurate, but is not obvious to deploy them. Now, let's go to another case study. I want to classify the filling level of these bottles, which enclose, which stores some sodium chloride sterile liquid, because this is submitted to for intravenous administration, and I would like to avoid that the nurse goes every time to check what is the filling level, and this is monitored by a camera, and the camera is able to understand what is the fill level by itself. Now I handcraft the network, and I started with a ConvNet, which is about 1.2 million of parameters. By the way, in floating point, this is 5 meg. 5 meg, for example, the most powerful STM32H7 has 2 meg of flash. So definitely this solution is not deployable. However, it is accurate. Can I play with the network? Yes, handcrafted. So I start to play with stride in the convolutional layer. Then I start to reduce the kernels, to reduce, for example, also the number of dense layers, trying to measure a posteriori the model size and the accuracy. Now, followed by some experience and some intuitions, I can get at least a twofold reduction in the model size, still keeping the accuracy. Should I be satisfied? No. I can even pursue this optimization on this problem by mixing a number of kernels and further reducing the dense layer and play with the pooling in order to further reduce the parameter. They were 1.2 million, so 5 meg. now in this Tiny2 model, which nice accuracy, measure on the data set, which is public, I shown before, you can freely download, is about 7,000. 7,000, these, if I quantize to integerate, these are 7.6 kilobytes of flash, which is a very nice result compared to the 5 meg. Should I stop here? No, because I could introduce separable convolutions. And also I can introduce the twice convolution. Why? Because these are well known to be capable to reduce model size, to reduce complexity, and therefore to have even a tinier model. But this is based on experience, on knowledge, and therefore it's a time-consuming task. So what the message is here is that while before I was able to deploy automatically a neural network which was pre-trained, now to design and to tune such a neural network in terms of topology, mix of layer, hyperparameter, I am doing that handcrafting. And this suggests the gap. Then I can, the deployment can need also to serve another need. For example, I can demonstrate on a given data set that I can obtain a tiny network with a very good accuracy. But what happened when I pulled on the field? Now, should I develop months of applications? Being a deep expert on embedded applications, which takes months to go on the field and to test? No. We introduced a methodology that, since the deployment is automatic, I can connect, I can mimic, I can use the Nucleo board with a STM32 microcontroller as an hardware accelerator. And this is not a joke, of a PC, because in such a way I can connect any sensor that I like, for example, a webcam, and start immediately my field trials. In this case, on the STM32H7, so here the inference per image is about 4 milliseconds. This is an 8-bit post-training quantized pipeline between the ones that I shown before, or I can, thanks to the exercise of fine-tuning the parameter, the mix of layers on an even more challenging tiny board, which is featuring an STM32F3, which is a Cortex-M4 with 16 kilobytes of RAM and 64 kilobytes of flash, very tiny. The previous one, 1 megabyte of RAM, 2 megabytes of flash, 480 megahertz, while this is 72, and do the same. And with this methodology, I can rapidly start field trials, targeting very different microcontrollers. These are the too far edge of the family, the most powerful, the big guy and the little boy, which anyway represent the variety of the microcontroller one can choose and pick up. But once again, the deployment was automatic, but the network was developed with an handcrafted process. So let's abstract now. Let's go back. Let's consider what is the end-to-end ecosystem we are playing with. Okay, because otherwise we are finding solutions which are optimized to a certain space. So if I suggest to consider the following pipeline when we develop machine learning solutions. First of all, we start with the need to acquiring data. Data can be acquired from real sensor or from synthetic sensor, and this can be a good method to have enough data to shape a problem. Then I need automatization everywhere. I need to automatize the data labeling and the data augmentation process, because handcrafting manually a data set is the greatest part of a project, 80% at least, if not more. Without counting the update of the dataset thanks to the field trial findings. Then I need to apply automatically for NAS and HPO, which we saw it's a very complex task. And then we need also to optimize the graph that I'm obtaining before to feed backend tools, in order to allow deployment. Backend tools, you got an example of what STE produce, STM32Cube.ai, but there are also other backend. Now, so look to all of these from a perspective of an embedded developer. And this is exactly some embedded developer told me. How can design a resource-constrained machine learning productivity? Not deploy, design. Because deployment is fixed, but the design is still a source of the gap. Now, look at the community. We have mainly 3 communities around the world. The C++, C# embedded developer, more than 10 million. The Python developers, about 7 million. By the way, there are no exact figures. Let's look to this in terms of order of magnitude. And the Java developer, which are experts on object code development, and they can slowly migrate to the Python developer. Why? Because Python developer, a subset of those are AI developers. How many? About 22,000, 300,000. But if we look, if we couple this population on the pipeline I was previously suggesting, you see that the C++ developer pose themselves in the backend area. The AI developers, which were, as I said, much less than the C++ developer, are 3 orders of magnitude less. And there is not only an automated machine learning gap, but also there is a resource gap. So you can start to understand why I had this question from the C++ embedded developers. Okay, they need to support. They don't have time to learn, go back to the university, take courses. They don't have time because they are under pressure to produce a new solution and to go to the market. And therefore, if a person like that is not supported, you know what happened? Simply wait for good times and will not invest on machine learning. So this is the dilemma we are facing, and therefore we need a bridge. What is the bridge? Is an automated machine learning design methodology, which is capable to produce solutions which are deployable. So all of that I said before is to come to this point. However, there are further requirements I would like to mention. First of all, this is the one that I like at most because I worked and I had the privilege to work for some time in the ISO organization where Leonardo Cariglione was the convener. Interoperability, the documented agreement reached by a group of individuals who recognize the advantage of all doing certain things in an agreed way. I'm not speaking about ISO or Kronos or any other type of standardization committee. We need interoperability in the sense that the community, the AI community, and the C++ community, they must find an agreement, a way to exchange information. Otherwise, productivity, automation will be at risk. We need scalability because the solution needs to cope with a large number of devices. Imagine the famous figures about IoT projections in terms of tens billions of devices in the IoT by 2020. These IoT units feature lots of sensors, so the number of deployable sensors are hundreds of billions. So we need huge scalability. We cannot find a solution which serves only a few customers. We need to find solutions which scale along the number of devices, not the number of customers, which will be deployed on the field. Third, automation. This is clear. We need to automate. We need to automate the process as much as possible in all the steps. And then we need to be productive. It's not more acceptable that embedded developer takes months or invest years in terms of acquiring skills in order to go to the market with an AI solution. That's not going to happen. It's not happening. Didn't happen in the past because they don't have time. Therefore, they discourage. Productivity is a must, is a key word. along us with the interoperability automation. And I think our efforts on STM32Cube.ai and the Specify Studio.ai are a contribution along that path. We are looking to NAS tool that definitely help the problems of those people, of the embedded community. So there are a lot of related work. You may ask, but is it possible that nothing happened and nothing exists? Yes. And this is one of the focus of the TinyML community. TinyML community, the largest community, which is concerned on resource-constrained device, able to cope with tools, algorithm, software solution, hardware solution, in order to address the milliwatt or below power range envelope, which is important and is fundamental for resource-constrained devices. And the acceptance and the growth of this community is just awesome. In few years, thousands of people joined. Even more students started to learn techniques, tricks, courses on TinyML, and this is really something that personally I didn't see happening since the old MPEG time, the times where standardization of audio and video took place. So it's really amazing what happens. In terms of solution, yes, in terms of solution that are able to address the tiny NAS domain, there are a lot, but these are research solutions. At least a few of those are able to cope with microcontrollers. Others actually are not really concerned or improved on microcontrollers. And once again, these are based on techniques that were listed at the beginning: Bayesian optimization, evolution search, and so on and so forth. What are the constraints? Memory, you see, model size, latency. These are RAM usage. These are the constraints, exactly what I was mentioning before, in line with the capability of our tools. And then I started to play with the Newton AI solution, the free solution, that I invite you to experiment on a number of tiny case studies. Infrastructure monitoring, electric grid. If you enter in the tool, you will find clearly. But look at the number of coefficients. We are observing few tens of coefficients, few hundred of coefficients. A machine learning pipeline with so few coefficients, by construction, is a tiny pipeline. And then it's obvious to show that the model size is 1 kilobyte or even less. And also the footprint of the deployable model is a few kilobytes. And this is relevant to solve, to address what I call in-sensor neural computing. And we will have a quick look to what I mean about that. So let's introduce a new challenge that will affect certainly the space of automated TinyML design, deeply quantized neural network. This will certainly extend the search space. So the NAS, HPO, will become even more complex because now we are putting on the table more and more hyperparameters. One example, Kukeras. Kukeras is a library set as drop-in replacement of Keras API, which sit on top of Keras, which sit on top of TensorFlow, and allows you in a quantization-aware training fashion to deeply quantize neural network. Let's have a look at an example. This is a ConvNet pipeline, quite trivial. First of all, to become a Kukeras pipeline, I needed to introduce quantized convolutions and quantize dense as a quick example. Then I needed to quantize the weight. In this case, I am introducing fractional arithmetic, which means the format QMN. In this case, means 0-bit for the integer part, 7-bit for the fractional, symmetric, or binary. Therefore, it's an heterogeneously quantized neural network where some layers are binarized, where some kernels are binarized in different way. And I can play with the full range between 1 and 32 integer bit. Same for the biases. And now I can also introduce quantization of the activations once again. And some will also I can play with binary activation, depending on the pipeline I want to shape and the performances I want to achieve. And in fact, this allows to achieve, in this example, a very tiny model, which is fully profiled in complexity. And if we mix binary operations with 8-bit operations, hopefully without floating point operation, definitely the power consumption is set to be very low, because then I am starting with a tiny model, which costs very much less. And then if I implement on a target execution, this will underuse a microcontroller, and then for sure I will save power consumption. But now we have facing a new opportunity. As I said, let's step for a while before to what I was saying. There was a prediction that in 2020, 50 billion IoT devices were permeating the world. If we put a few sensors inside, let's say 10, you can imagine that the opportunity are to scale to 100 billion of sensors. Okay, can they support machine learning and artificial neural networks? Yes, and this is what I remind as in sensor neural computing domain. But developing a solution for this domain is really a tough exercise, because we have constraints that are pushing in completely opposite direction. The first, who drives the implementation in terms of silicon node? The sensor, not the LSI, which means that I cannot play with the FinFET 7, 6, 4 nanometer. This is totally out of scope, because we need technologies which are parsimonious in terms of implementation for the node itself. Power consumption, microwatt. I cannot add the logic which is more than the sensor itself. The sensor in a certain mode consume microwatt. The logic, the AI logic, need to consume a microwatt. There is no point to put together microwatts with milliwatts. These are different order of magnitude. Memory, few kilobytes. There is no way. There is no space for a lot of memory. And there is no space to use the silicon node scaling to have the opportunity for more silicon area. Same silicon die of the sensor. You have to start thinking and considering that we are using a micro machine and putting close to it logic, not logic with somewhere the sensor. This is not integration in package. The package must be standard as the sensor itself. And then we need also compilation techniques in order to deploy machine learning on it. So and this has to be one product. It cannot be fragmented, source of compromises. Like, look, I put a sensor in 130 nanometer die close to a silicon, which is 7 nanometer FinFET, because the cost structure is totally out of any sense, and then it will not scale. And in fact, we introduced the ISPU. At the last IEEE Sensor Conference, a colleague of mine introduced this solution, which is essentially a sensor which integrates in a very small amount of kilogate, 8 kilobytes, 40 kilobytes of RAM for both program and execution, with an advanced DSP that we designed, which is very fast, with a compiler which is coupled. And the benchmark are confirming the goodness of this approach. If a network is fully binarized, in the case the sensor is, for example, an event-driven sensor, the improvement versus a floating point neural network is 10 to 20 in terms of size and execution time. If we mix and match floating point and binary operations, then the gain lower, but is still significant. Now, we go to a fundamental question, which is very open in my mind. We need a productive tool. I think this is very clear from my presentation, that is able also to deal with deeply quantized neural network. And I'm certain that in the next year, there will be further revolution in that respect, because there are technical advantages which are amazing, such the one that I just shown, in order to enable deployment on hundreds of millions or billions of sensors, which are the opportunity we are facing, we all are facing. So thanks so much for your time. I apologize if I took too much. It was for me very exciting. I hope I transmitted at least my feeling on that, because the topic is amazing and certainly will be open to revolutions as this session is titled. Thank you so much. And I'm open to take questions at any point in time.
Awesome, Danilo. Thank you so much for that. Yeah, feel free to drop in any questions that you may have, and we'd be happy to answer those. And you can leverage the Q&A box as well. So we'll just give that a few minutes. And then next up for today's session, we will be having Sumit Kumar, the founder and CEO of step2stem.com, and hardware hacker as well, up next to speak. So we'll just we'll give it a few minutes here while we look at that. Excuse me. And yeah, my name is Andrew Glutt. I am the Director of Strategic Partnerships here at Newton AI. So fabulous session, Danilo. And next up, like I had mentioned, we will have Sumit. So hey, Sumit, welcome. Appreciate you joining us today. How are you doing?
Yeah, I'm doing fine. So can you all hear me?
Yes, we can hear you just fine.
Great, awesome.
Yeah.
So yeah, I'm just going to start presenting my screen. Just a second. Can you see my screen? Okay.
Yes, yes, we can.
Awesome.
Yeah, so before you get started, perhaps maybe you could just share with us a little bit on kind of how did you start your journey with Tiny Machine Learning. Would be awesome to hear from you.
Yeah, so actually I explored this platform called as Hackster.io, and I had been joining this platform since 2019. So it was an awesome journey. There are lots of contests coming up. And exciting thing was in 2020, I just got a contest from sparkfun.io, and they were conducting a contest on TinyML. So it was awesome for me to learn something new, because I just started pretty late in technology side. I was just focused on the school side before 2019. So you can see TinyML came to me as a blessing, that I started exploring more and more into the technology side, and exploring how can we make machine faster, intelligent, and make some cool projects to maybe participate somewhere and all those kind of stuff. So that's how I started this Hackster community. And this platform is actually very cool. You get to learn from many people. These hackathons are quite fantastic. They get to make you explore new hardware, new kind of design, and all those problem solving skills. So it was great for me. And I hope those who are attending this webinar, they will be also joining this platform. So yeah, so this is all about I started on Hackster.io, and it's a cool community, and I enjoy it. Most of the time I spend here searching for project, getting some inspiration. And today I'm going to talk about ARIC, or that is called as Agricultural Record on Electronic Contracts. So basically, I just started exploring this problem statement last year. The problem is very huge, actually. If you see in the agricultural sector, it is very important, for the products or the agro-based chemicals to get to the farmers at right amount of at right time. Otherwise, the whole you can say the hard work or like the manual labor of the very months would be destroyed or like will be like futile. So taking into like account of those, I just wanted to explore like what kind of solution we can build there. And I also participated in Bear and Bear hackathon. So Bear and Bear hackathon. So it was also like a good guide for me to like explore this field. So other thing is like when you talk about agricultural platforms, like there are a lot of challenges in transit, like the collisions, violent falls, extreme temperatures, and due to that, there is a spillage or like the container might burst. And you know that those chemicals are like explosives, some kind of explosive, also pesticides and all those chemicals. So for each problem, I think when we mix different technologies together, we come up with a like an ingenious solution. We just try to solve a different problem in a unique way. So this is how I'm going to talk about Newton TinyML, how I explored this platform, and how I'm going to like share my experience over it. Couple of days I have been working on TinyML platform. And also the thing is like there's a lot of opportunity in this field, because every company all those agricultural companies, like agro-based chemical companies, they are looking for a solution because there has been a huge loss due to this problem. So I'm just going to go over that after this. Sorry. Yeah. So this is the project which I started, and like the problem, as you already discussed, most I'm from India, and like most of the pesticide, insecticide we just hear are counterfeits, or they're not very real ones. They're just being counterfeit, and government is trying to make a huge stride to control those. But unless there is a new technology developed to solve that problem, nothing is going to help. No counter solution is going to help now. So how we are going to implement this solution? Our solution is going to talk about each device. There are a lot of products in the market. Agricultural companies, agro-based companies, they make huge products, and to solve that problem, we are going to explore what kind of design we can work upon. This is a smart label layout. Actually, this is going to be a smart label which we can stick on any package, and that would be delivered to the farmer. And already I explored a few days on this. So I'm just trying to demonstrate a prototype. So we are using ESP32 module, which is very cheap actually. So that's why I just went for these, and like the MU280 sensors and all these air quality sensors. So and there's also why I'm going to use Newton AI, because as you already discussed, we just want to make it a low cost way. Otherwise, the farmer would not be able to afford the packet, as well as the technology coming with it. So it is going to be very expensive. So Newton AI actually make it very much possible to run on the cheapest MCU available to them. And I saw it it is able to run on 8 bits, so it can control computational efficiency as well as the power consumption. So that's a good fit actually, because traditionally we have data loggers which we use in the logistics that log the data like temperature, humidity, but getting a efficient solution is a distant future we are seeing in this space, agricultural product space. So TinyML using Newton AI platform looks very tiny, but there's a lot to explore there. The platform is very unique, and I can show you how easy it is to get started with the TinyML platform. So it has been my choice of framework for this prototype, because it was very much intuitive for me to learn about this, because it is something new which I haven't experienced earlier. I had been doing with TensorFlow Lite, Edge Impulse, but this one when I ran into the fundamentals, how this solution is working, so it was quite intuitive, training the neural networks, just not taking a structure and then optimizing it, but rather adapting to the data. So that is very much unique, I just found in this space. So just a quick demo. I'm just going to show you how I how it is easy to get started with it. So first of all, you need to have a account, and thankfully Newton AI platform is giving you Gravity plan that is free of cost for all, and make sure you just try it out. because it's something cool. Sorry. So once we are into the platform, and you can see like it's getting ready. So meanwhile, okay. So we are going to add a new solution because adding a solution is the first step. It barely takes more than 3 steps. It is already this webinar is all about 3 steps, or 3 steps to perform a machine learning with Newton AI. So just talking about the 3 steps. So the first step is going to be adding a new solution and adding a data set. So this is how it is done is, let me explore this. So you just add a solution and the description, and then you go on to adding a database. So I'm just going to show you actually. It is okay. So once we are into the training data set, you can upload your own CSV format file, or if you have in your storage, data set storage, so you can select any of the data, or you can choose from the preloaded data set as well. So this is very much cool actually, I found, with the preloaded data set, because when we are talking about TinyML, the most the problem which I face thinking of an idea, I got lots of idea to implement using TinyML. But the only thing that I just give up on many solutions because I don't get valid data, or I'm unable to understand how do we collect data for that, because it might involve too much complexity. So getting correct data and a good amount of data is actually a big problem when you're trying to solve a problem using TinyML. And sometimes data collection takes a huge pain as well. But if you're trying to explore some clear data set, it is already providing many data sets, which is very much cool to try out with. And they're very much tested data sets. So we're going to select from our storage, which I had used. So this is the data set, and you can preview this data set actually. So we got 3 columns, sorry, and the condition column is actually going to be the classification. So we record the temperature and humidity for 2 conditions. One is either extreme condition, that is going to result in condition 1 value. That means it is abnormal temperature. That is going to classify that your product is not going. Product is kept in a place which is not suitable temperature, which is not a suitable temperature for the product, because all those chemicals, like agricultural based agrochemicals, they have the certain temperature ranges, and they should be stored within those ranges. So that is very much important during the transit. So this is how we add a data set, and then we just move on. So this is the first step, and the second step is to select your target variable. So this target variable is actually kind of what you're looking for what you are just trying to use your data set for. A kind of, you can say it is going to be for X, the value Y. So it is a dependent condition you are trying to test. So it is a dependent variable actually, to say much more in the terms of maths. So now we get to select the TinyML, and yeah, this is the cool thing. You can select the bit depth. So you can either select the 8 if you are just too much conscious about the memory and all those power consumption. So better go with the lower one, 8-bit. And I personally felt that there was very little, or I think no, minimum loss of accuracy. So whichever you go, it is not going to matter. The only thing is you should have the right problem, right target hardware actually. Otherwise, 1632-bit works on all the new development kits, and then you can just try to start the training. So I have already trained it. So training takes some time, and plus you get a feature that once the training is complete, you can easily get a notification through your mobile SMS. So I think it is quite cool. So I'm not going to train it now because it's already trained. So let's explore it. So the training took 5 minutes and 18 seconds. So this is my training result. It was quite accurate, 95% accuracy. And the other thing is you get to good advantage over like checking like your progress over the training and the heat maps, correlation maps. So that's quite cool. And it all depends upon data type, like data set. Like if your data set is something different, so you might explore, get more kind of graphs and all those like feature metrics. So it is all dependent upon data set. So my data set was very clear and it was a binary classification. So it resulted in like the distribution, like the variable distribution and the heat map. And then we go to the prediction. So this is cool, actually, historical model to data relevance. So this is what we had been like Newton ML has been quite good here, because this actually shows you like your data is how much relevant to new kind of like test data. So whenever you see you're losing some accuracy, you can retrain your model with new data. So that's quite cool, actually, because you get to know how your model is performing in like real world test case, and like how it is going to perform further, and then you can retrain and apply your logic on that. And you got the prediction, the REST API access, which makes it infinite possibilities to implement in different programming languages. But we are going to look on the downloadable solution. You're going to download the solution, and like it is going to download a zip file, which is going to have this kind of structure. You can just see the file structure. So the model.c is actually the model file that is going to have your model memory and all those things. And these are the two important files that is performing calculation and all those like memory crunching task. And they got the user app C and user app C, that is the callback file. So whatever like inference loading this model, all are going to use the callbacks declared in the user. So you get a pre-deployed template, actually. Pre-made template is already there, and you can easily use it so that you can configure your model pipeline for your own. So I have tested on 2 devices. Currently, I tested on ESP32 and BLE33 Sense. So based on the code, it should actually work on any hardware. 8-bit. So the model was trained for 16-bit. So I don't think it would be having any problem working on any 16-bit device. So just to go more into the details of like this TinyML, yeah. So our model has only 120 coefficients. So I remember my data set had more than like 2,000, rows. So it's quite impressive, actually, because earlier I tried TensorFlow Lite for my model and like for my projects. So it was not quite small, and the size is also very small. The embedding size is also very small, less than a kilobyte. So it's pretty much like good, actually. I just found it very much low of memory footprint. So this is how the structure is being defined here. So we just get the like callbacks. So this is the let's go to this. Okay. So first of all, you need to initialize the calculator int function that is going to load your model into the memory, or better to say in the flash, and then you're going to get the app model info. So we just ensure that the model is correctly loaded or not using these callbacks. So these callbacks are defined here, and you can see when you call the app init, it should call the calculator init that is defined in the calculator.c file. So on calling this function, it just tries to load the neural net structure into the memory, and then you got neural network free. So when you call this function, it is going to free the neural network structure, which is which the user has been using. And then you got the important thing on, yeah. So here goes the important thing. So this app.run inference, you just pass the sample. So you just prepare the sample as you did for the training. So it should match the training data set which you have used, like the first column was humidity, then temperature, and additionally you add a bias to this sample. And once the sample is ready, you can just run this, run for the inference, and then pass the sample to that function. So this is just like a condition we had put, like 0 is the normal condition, 1 is abnormal condition, and then we have the unknown condition. So once you are done, you can just free the memory and then again you can reinitialize from here, like loading the memory back into loading the model back, and then so this is like you just do an iteration, and then you just try to get the model like output. So you can see it is this was the output result I had been like testing. So it is not quite complex. It's very simple to understand how the model is working. The only thing complexity might be like choosing right data set for your project or making a correct data set. So that might be a challenge. Otherwise, like what cool you can build. So I found that there are a lot of cool things which we can build. And whenever we talk about whenever we are talking about TinyML, the only thing that comes to my mind is which should be like implementable. It should solve a real problem. We already got a big like a supercomputer solving a big huge problem for the like the astronomers, for the weather scientists and all those. But when you're talking about the TinyML space, how it can solve like the daily problems, that should be the main focus, maybe according to me, in my opinion. So you can use it for the freezing of get like for the Parkinson disease. So that's a very good use case you can use. Using the accelerometer and the gyro sensor on the hip and leg and then finding it. Or maybe force and torque measurement on a robot for failure detection, appliance energy uses, or like alcohol content to predict the heavy drinking episodes, and many many more like this. So you can keep this list growing in the comment box so that I can also be inspired and then try to work on some new models. So it would be very much cool. So just grow this list. So coming back to this, how this is actually solving the problem. So we are also trying to explore blockchain into this. So for blockchain, I'm using DAML. So DAML is quite like you can say like easy for like preparing own like a set of data and file structure, like not data and file structure, sorry, but preparing like the proper like suppose like we got the package label template. So whenever you're talking about an agriculture product, the farmer has the right to know the information about the company, the product usage, the harms and the negatives or the side effects. So in order to make that in a like a immutable structure, so we just need a blockchain one. So that is DAML going to provide us. So we just don't want it to be fully transparent. We want it to be selective transparent. It means that it should not be like a fully visible to all, but like it should be a stepwise process. The company should be able to intervene. The Agriculture Commission should be able to intervene in between if there is a like a alert or something. So this is how this was the problem statement which I tried to solve. And maybe if I'm able to like get more on this, I'll just try to finish this project so soon. So I hope you like the project, and if you have any questions regarding training the model and like using TinyML, so don't hesitate to ask. I'm always like happy to help. Yeah, thank you.
Awesome. Thank you so much for sharing your experience with your use case, as well as implementing the model. I thought that was really cool. Definitely a lot of fascinating projects you're working on. We're excited to see you continue to explore new models and everything like that. So a few questions did come up as you were speaking. For the preloaded data sources, we do have some of those from Kaggle. That is correct. So we do have quite a few famous data sets. Another question was, if I want to check every step, can I see what are behind the graph/step? So I believe when you were going from the dataset tab to the training tab and the prediction tab, I think there's a question of, can I see the step in between? So traditionally with a lot of different solutions, you'll have to do different things like hyperparameter tuning and whatnot. With Newton, we've gone to simplify that process. So you're not actually able to see every step. We also had a comment, the data visualization is cool in Newton, so appreciate the comment. And then also, does Newton contain images or does it support object detection? So as of now, We do not support images or video. Right now, all of the problems that we're solving are with tabular data. So if you're able to extract your data from Excel and upload it into the platform. So yeah, those were the a couple of questions that came up. And yeah, so appreciate you sharing your experience. Very cool stuff of what you're doing. And now we're just going to take a little bit of a quick deep dive into Newton and another use case that we did as well. So let me just pull it up. Awesome. So how do we build and embed models, 1,000 times smaller in just 3 clicks? So we have just some questions, what if we were able to create the solution without having any technical expertise? How can we create a model in just 3 clicks? How can we find the most optimal model in one iteration? And how can we produce smaller models? How can we have faster inference times, eliminate the need to perform any compression without compromising accuracy? A lot of times what we see as we do compression and quantization, we see a decrease in the accuracy. And on top of that, how can we explain why the model makes every single prediction? So, some of the data and analytics that we saw in the explainability office during Sumit's demonstration, we also have the ability to look at each individual prediction and adjust the values to see how it would influence that prediction. Additionally, how can we address the ability to bring different AI models into production faster? Oftentimes, we can work on models for a very long time, but actually don't bring it into production. That's not getting the return on investment. And so, how can we build fast, build once, and not compromise on the accuracy or our business requirements? So, when we look at the framework of Newton, we take a neuron by neuron structure growth. So starting with one neuron and building and doing cross-validation across the way. So we also eliminate the need to, do neural network architecture search. We also help reduce the model size without having to leverage some of the other techniques on the market. And also the models aren't compromised by the compactness. And so, when we look at, what are the kind of requirements of the hardware devices and what models we're able to put on here. Here's a little bit of technical information about the characteristics of the devices. And then we did some benchmarking with the Newton platform as well as TensorFlow Lite and Edge Impulse. So you can see at the top the different results for area under the curve, the size of the model, the number of coefficients, RAM usage, etc. So here we can see very good results, very small and compact. When we look at the traditional way of creating models, we'll go through model creation, we'll do manual search, we'll do compression, and then, embed it into the microcontrollers. So this could require a lot of different skill sets and a lot of, different skill sets. And then when we look at Newton, we're able to create the model automatically and embed very quickly. So we only need the skill set of one person. And similar to the use case that you were sharing with us, Sumit, we created a model with Newton in order to predict whether food was spoiled or not. So this device is looking at different gases and then predicting the spoilage. So let's just take a quick look at that video now. So here we're going to look at creating the model. So as we saw before, we'll just create the solution. And now we'll name it food quality. And we can either upload the data set from our computer or from our storage. It's going to quickly look at the data set and make sure that it's valid. Now we select the target variable label. Here we're going to turn on TinyML and then select the bit depth. So we have 8-bit. Here it's going to now train the model. Since that takes a little bit of time, we already have one that is pre-trained. So let's take a look. Here you can see information about the model, as well as the different coefficients and size of the model. As we kind of saw earlier, we will then download the model. Now we're going to copy the downloaded model to the sketch, and with a few different business logic as well. And then we'll compile that, the sketch, and then deploy it. So here we're looking at processing the data. So what we're going to do is embed it and then use data to predict. And then once we've done that, we then will feed it new information. In this case, green, it's predicting that the food is not spoiled. And then in the next prediction, we can see we've run it again, and now we've predicted that the food was spoiled. So as kind of Sumit had shared earlier, with just a few clicks and not a lot of technical expertise, we're able to deploy a model very quickly. So those questions we posed earlier, how can we build a model without expertise? How can we run inferences faster? With Newton, we're able to do that all very quickly. And so some of the challenges that Blair shared with us earlier, limited knowledge and availability of resources from an ML perspective. How do we integrate those large models into edge devices? And then also evaluating the quality and understanding the logic behind the model. So with Newton, we're able to accomplish this with our zero-code AutoML platform for non-data scientists. And the framework in which we leverage will create very compact models. And the explainability office helps give us information about the models that we build. So I'd encourage all of you to go to this link or scan the QR code and go ahead and build the model yourself. So this week we are having a competition. So feel free to get in there, try it out, and you'll be able to build the same model that I just demonstrated. So I'll just leave this up for a few minutes while we get Q&A going. So yeah, feel free to try out the platform. And then, yes, Sumit, Danilo, if you have any other comments or thoughts that you'd like to kind of add as we wrap up, definitely encourage any comments as well.
Yeah, Andrew, I just wanted to, relay that tomorrow the event will be at 8:30 IST in Indian time. It will be at 8:30. So, like, if people are going to join in different time zone, so they can convert those international time to Indian time and see It's at 8:30 p.m. IST.
Okay, perfect. Thank you. So I appreciate it.
Thank you.
Yes, meanwhile, we are waiting for questions. I would like to mention also that we have prepared a very intensive program for you, as Soham mentioned right now, that tomorrow you will have masterclass of how to build the model manually, and the second day also you will learn regression and how to build front-end solution. And in the final day, this Friday, we will show you end-to-end process of how to create an embed model, but in detail. So you can go step by step with us. And even you haven't done it before, never, after this session, you will be able to do it with us and by yourself. So please join us. Please join us for these next sessions. And now we have some, I think, some comments and some questions in the chat. Andrew, can you please?
Yeah, absolutely. So we have one from another one from Timothy. So how many ML algorithms are supported? And can we have a comparison of ML algos in Newton AI? So traditionally, like I had mentioned, some of the other solutions out there will take all of the different algorithms that are available on the market and find and pick the best one. Newton is leveraging our own internally patented algorithm. And then from a comparison perspective, as I was kind of breezing through the presentation, we did compare Newton versus TensorFlow Lite and Edge Impulse and a few others. We also have a series of different benchmarks on our website as well, across a lot of different use cases, some from Kaggle as well. And then we had...
I will share now in the chat the link to our benchmark, so you can check it up. And of course, you are very welcome to join our Slack, where we post there all materials, all the presentations from today will be posted there, as well as video, all records. And we have a growing community, and you can make your, like a network and ask us questions, and also participate in our educational activities. So please welcome. I think I already shared the link. Oh, thank you, Jim. Excellent demo. And thank you. Thanks for the link to the data repo, Sumit. Yes, Sumit, thank you so much.
Yep, and there's also a comment about opening up a big opportunities in a lot of different fields. Absolutely, from a TinyML perspective, the community just keeps growing and the technology keeps evolving. And so we'll continue to share those experiences and bring in industry experts to share those experiences and use cases and help you along your way in your journey. And as Yulia mentioned, the Slack channel is a great opportunity to connect not only with us but your peers as well. So feel free to check that out. And ideally, you'll also see other upcoming events that we have as well. So yeah, it was a pleasure to have Sumit and Danilo as well as Blair today, as always.
So if you didn't write your questions, you are welcome to do it in our Slack channel now, YouTube and LinkedIn. Please join. And as I said before, we are waiting for you tomorrow, 2 hours earlier, in order to have a masterclass with Anubna. Say hello, Anubna. I know you are here. And let's learn and enjoy. So I think it's time to say goodbye to everyone. Thank you again for joining us tonight or this morning. For Andrew, for you it's early morning, I know. Danilo, it was amazing presentation. We got a lot of requests. If you can share with us your decks, and we can post it in the Slack. So more people can learn from it, because I think maybe from the screen it will be a little bit difficult to see everything. So we will be very appreciated if you can share with us.
Yeah, thanks so much for the opportunity. It was so much exciting to be with you today and to speak about this amazing topic.
Thank you, Danilo. We will invite you more. I am sure that you have a lot of knowledge and experience to share with us more.
Danilo's LinkedIn ID on the chat itself, and also on LinkedIn. Like, I just got two, private messages. So can I just put up that in the chat?
Do you mean some questions from LinkedIn? Let me check it quickly.
Oh, he was just asking if, Danilo, do you mind if we post your LinkedIn and chat so that people can add you?
Sure, no problem. Sorry, I didn't understand. Sure, no problem.
Cool.
Thank you so much.
So again, thank you so much. See you tomorrow. Have a nice evening, day, and morning maybe.
All right, bye.
Bye-bye. Bye to everyone.
Record.